In this video, the data-driven stability margin for linear multivariable systems will be introduced. Nowadays, most areas have the following two features. First, uncertainty is ubiquitous and inevitable. Second, high safety requirement is needed. Thus, stability and robustness become the first two concerns. As a quantitative indicator of relative stability and robustness, the stability margin is widely used in control engineering. The stability margin is important. Too small stability margin may lead to bad performance or danger. For single input, single output linear time invariant systems, the classic stability margin is well defined and understood. It has many advantages. However, the SISO stability margin is not applicable to MIMO systems. There are some commonly used MIMO stability margins. However, these stability margins are mostly model-based, and somewhat complicated. They are not easy to be used by control engineers. Thus, we propose a data-driven stability margin. Consider the closed-loop system including the plant and the controller. Next, take the input uncertainty into consideration. The figure on the left side becomes the right one. Then, the objective is to determine the gain margin and the time delay margin for the closed-loop system. Next, the system can be displayed as a feedback connection. In order to explicitly display the gain margin and the time delay margin, a loop transformation is also done. The remaining part except the uncertainty delta is denoted as Ri. It can be seen that the uncertainty delta is in series with the transfer function Ri. According to the small gain theorem, a theorem is drawn to prove robust stability. Next, a data-driven method to get stability margins through frequency sweep experiments is given. The output responses are collected at the point W by injecting frequency sweep inputs to the system at the point Z. Based on the input-output data, one can get Ri. Then, stability margins can be obtained based on the small gain theorem. The data-driven stability margin is straightforward and can be acquired experimentally on model-free occasions. Furthermore, it can make the online stability margin evaluation possible without breaking the loop. Next, we will show a case study of a two-input, two-output system. The considered plant is G of S. First, the SISO phase margin evaluation is given in reference 1. The closed-loop system needs to be broken at the point P to obtain the open-loop system. Then, the stability margins are obtained based on the one-loop-at-a-time analysis method. However, a perturbation meeting the given phase margins leads to system instability. It concludes that the one-loop-at-a-time analysis method is unreliable for MIMO systems. Next, the data-driven MIMO stability margin evaluation is carried out. When a gain or a time delay perturbation meeting the given stability margin is added into the system, the closed-loop system can still keep stable. Next, we will show a frequency sweep experiment of an F450 quadcopter. The indoor fixed multicopter platform, which uses a specially built stand to restrict the motion of the quadcopter to 3 degrees of freedom without position change. Additionally, a 50 grams load is attached to one of the quadrotor arms to enhance the system coupling. The gain margin and the time delay margin can be found as 0.3608 and 0.0209 seconds. Verification experiments for the obtained gain margin and time delay margin are also carried out. The verification results are that the gain margin is around 2.5 and the time delay margin is around 0.025 seconds. The frequency sweep measurement results are a little smaller than the verification results. Although the obtained data-driven SMS from frequency sweep tests are a little conservative, the system can guarantee stability under a disturbance within the obtained data-driven stability margins. That's all. Thanks for watching.